In this lesson, we're going to be graphing y equals sine x and y equals cosine x. We're going to start out graphing those on the calculator to take a peek in to see what they look like, and then we're going to end up graphing them by hand. So go into our calculator. Let's first make sure that we're in radian mode. When we graph trigonometric functions, that's the mode we want to be in. So put your calculator in radian mode. I'm going to go to y equals, and I'm going to type in sine x. All right, now I'm ready to graph, but I'm also going to want to look at the zoom key. So let's look at the zoom key. We're used to the zoom standard window where when the graph appears, we know we go from -10 to +10 along both the x and the y axis. But sometimes it's helpful to use the zoom trig window. So I'm going to go down to zoom 7, press enter. So this is y equals sine x. We can see that it's what we call periodic or cyclical, that it's just going to repeat if the graph were to extend off the screen. It has peaks and valleys, or highs and lows. We usually call those maxes and mins. To get an idea of how high or how low this graph goes, let's go back to the window setting. To see how high and low it goes, I can see that the zoom trig window is set along the y-axis to be going from -4 to +4, and we have scales or tick marks at every 1. So I'm going to go back to the graph, and I can see along the y-axis that I count off by 1s. It looks like the sine graph goes as high as 1 and as low as -1. All right, let's also take a look at the horizontal feature of this graph. So I'm going to go back to window. All right, the x-min and the x-max go from -6.15, etc., to +6.15, etc. This is basically close to -2 pi and +2 pi. The scale is actually pi over 2 as a decimal. So I'm going to go back to the graph, and it looks like I'm going to go from x equals -2 pi to x equals +2 pi, and every tick mark represents a half pi. So I can kind of see from the origin, if I move to the right, at that first tick mark, that's pi over 2. The second tick mark would be pi. This third tick mark would be 3 pi over 2. So it's kind of good to know the structure of the sine graph by looking at the window. All right, let's see how the cosine graph looks. So I'm going to go back to y equals, and I'm going to change my function to cosine. I'm still in the zoom trig window, so I don't have to do zoom 7. Let me just hit graph. So cosine has the same shape as sine. It's just been translated or moved or shifted a little bit over, either left or right, however you want to think about it. Notice that cosine actually starts at the point 0, 1. We can say that it starts there at 0, 1, whereas the sine graph started at the origin. But they still have both the same characteristics where they're cyclical or periodic. The maxes are the same, y equals 1. The mins are the same, y equals -1. All right, so how did these come about, these graphs? So now it's time to graph these functions by hand. So what we're going to need is our unit circle, and we're going to create a t-chart. I've already got us started with the independent column. Notice these are all angles. I start out at a -pi angle, and then I'm going by increments of 1/4. I end up at 0, and then I still continue to count by 1/4 pi until I get to 2 pi. So we've got to fill out these values right here. We have to populate the sine of x column. So what we're going to do is we're going to take turns plugging each of these angles in for x in the sine graph, or in the sine function, and then we're going to figure out what the sine is at each of these angles and populate this column. So that's why I said have your unit circle handy. All right, what if we're at an angle of -pi on the unit circle? Well, -pi takes us all the way over here. Since I'm graphing sine, sine is connected to the y-coordinate, so I'm going to take the y-coordinates of those points at those angles, and I'm going to put them in my t-chart. All right, the next angle is -3 pi over 4. -3 pi over 4 would be found right here. It's coterminal with 5 pi over 4. I'm graphing sine, so I don't choose the x-coordinate. Those are the cosine values. I'm going to choose the y values for sine, and I'm going to get negative square root of 2 over 2. Well, I'm not going to transfer that number into this box right here because I'm graphing. I'm going to go to my calculator and I'm going to change negative square root of 2 divided by 2 to a decimal. And I'm just going to keep 0.7. Actually, it's negative 0.7. So if you're interested, go to your calculator and find the decimal value for negative square root of 2 over 2. We're just going to round to 1 decimal because we're going to be graphing. That's the context. So we don't need a bunch of decimals. Just one will do to help us graph. All right, go to negative pi over 2 on your unit circle. It's down here. The y-coordinate is negative 1. Next angle is negative pi over 4. We're right here. This y-coordinate is also, again, negative 0.7 as an approximate. All right, so you guys just go ahead and continue grabbing all the y-coordinates as you, as you land on each of these different angles right here. All I'm doing is grabbing the y-coordinates at each of these angles. Notice the kind of how they repeat. Okay, so what did we do a long time ago when we're trying to graph something? We have a t-chart. Well, we're going to plot these as ordered pairs on a grid. So first I kind of observed that my angles start at negative 2 pi, go up to 0, and then they end at 2 pi in my t-chart. So that'll kind of help me build my coordinate plane here. So I'm going to have more values to the right of x equals 0 than I am to the left. I'm going to go ahead and say, well, maybe the distance from here to here is negative pi. So trying to keep that scale the same, I would say that positive pi would be here, and maybe 2 pi would be about right here. Okay, remember we're going by increments of pi over 4, so I'll probably go back here and split this distance up in half, so that'd be negative pi over 2. And then halfway between 0 and negative pi over 2, I'll put another tick mark. And then halfway between negative pi over 2 and negative pi, I'll put another tick mark. So this will be negative pi over 4, negative pi over 2, negative 3 pi over 4, and then we're at negative pi. I'm running out of room to label these tick marks, but I think in context we should see what the x values are at those tick marks. Let's do the same thing over here to the right of x equals 0. I'm going to go ahead and label that pi over 2 and put a tick mark here for pi over 4 and one here for 3 pi over 4. Halfway between a whole pi and 2 pi, we'll have 3 halves pi, or 3 pi over 2, and let's put the tick marks in between as well. All right, let's go back to our t-chart and plot these points. Well, the first thing I'm going to do is I'm going to kind of scan down the sine of x column, and I'm just going to kind of look at the numbers, and I'm going, well, it looks like the lowest I get to is negative 1, and the highest I get to is positive 1. And that makes sense because the range on sine would just have us go from y equals negative 1 to y equals positive 1. So I might say, okay, this is positive 1, trying to keep that same distance down here. This is negative 1. So our scaling doesn't have to be the same on both the x and y axis, okay, but they have to be the same along each of the axes. So we have angles along the independent axes, and then we have values along the y-axis. All right, let's plot our point. So negative pi 0. Negative 3 pi over 4, we're going to go down to about negative 0.7, so that'd probably be about right here. Negative pi over 2, we're at negative 1. Negative pi over 2, we're about at negative 1. That's going to be about right there. Let me fix that. Negative pi over 4, we're back at negative 0.7, so we want to line up horizontally with this other point. And then at 0, we're at 0. All right, so the graph is actually going to come down, pick up this point, it's going to bottom out at this minimum at y equals negative 1, and then return back up and pass through the origin. So let's continue plotting the rest of these points to generate the graph over here to the right of x equals 0. So pi over 4 would be at 0.7 about right here. Pi over 2, we're at a maximum of 1. 3 pi over 4, which is right here, we're back down to 0.7. And at pi, we're at 0 again. So the graph's going to come upward, reach its maximum, come back down. Now between pi and 2 pi, notice these values return to negative, so it's actually going to look like this part of the graph over here. I might do 3 pi over 2 first. That'll get me down here to -1. Okay, and between pi and 3 pi over 2, I have 5 pi over 4, and I'm at -0.7. Over here, I'm again at -0.7, and at 2 pi, we can see from the t-chart, we're back up here to 0. All right, well, let's make some observations about this y equals sine of x graph. Even if I were to extend this t-chart in both directions, above and below with angles, I'm just going to get the same pattern. All right, some things to talk about that we will be talking about with regard to trig functions is, especially for sine and cosine, is, okay, we want to talk about what's the maximum. Well, it's y equals 1. What's the minimum? Well, it bottoms out at y equals -1 for this new parent function. Okay, a big thing, too, is what is the period of the sine graph? And the period means what's the horizontal distance necessary for this graph to repeat itself. Well, if I started at the origin and followed the graph, it goes up, then it also goes down, it returns to the x-axis, but it's just going to continue its pattern. So what's the necessary horizontal distance to complete one cycle? Well, we can kind of think about it going from x equals 0 to x equals 2 pi. If I covered that horizontal distance, the sine graph would have time to repeat its pattern. Well, can I look at this graph from x equals -pi to x equals pi? Sure. Let's look at the graph from x equals -pi to x equals +pi. So if I didn't start at the origin and go up, if I started on the x-axis and went down and then went up, okay, we can see that, again, the distance between -pi and +2 pi is, again, 2 pi. So I have a repeat then after that, after pi, of the same pattern. So no matter where you start, okay, you have to travel a horizontal distance of 2 pi for that graph to repeat itself. And that might just be a different piece that you're looking at. So we call the period for y equals sine x 2 pi. All right, let's record down here what we call some key points. Key points. So in later videos, we're going to be wanting to transform these parent functions. Perhaps shift them up, down, left, right, maybe stretch them vertically, okay, or shrink them vertically. We might also be talking about taking this graph and stretching and shrinking it horizontally. So if we're going to do all those kinds of transformations, then it's good to kind of start with some key points, and we're going to have 5 of them on y equals sine x. We're just going to say when we go to graph transform sine graphs or equations that we're going to start with the ordered pair 0, 0, this point up here, which is pi over 2, 1, back down to pi, comma 0, continuing down, the 4th key point is going to be the ordered pair 3 pi over 2 and -1, and then to return to the x-axis to complete the cycle, the 5th key point for y equals sine x when we go to graph will be 2 pi, comma 0. All right, let's take a couple minutes and go ahead and complete this chart right here for y equals cosine x. We did see these graphs on the calculator and how they compared. So we do know that this graph over here for y equals cosine x will be very similar to this graph, but cosine x won't start at the origin. It's actually going to start up here and continue and draw its cycle. All right, so let's go ahead and complete this chart right here. So now we're going to graph y equals cosine x. All right, notice that in my t-chart I have all the same angles, but down this column I want to populate the cosine values at each of these angles. So we go back to our unit circle. We're choosing the x-coordinates now. So -pi, its x-coordinate is -1. -3 pi over 4 is next to my chart, so I'm over here. The x-coordinate is -√2/2. So we're going to record -0.7 for graphing purposes. Okay, I encourage you to pause the video and go into your unit circle and populate the rest of these values right here. Okay, now using these ordered pairs, let's come over here and do the same thing. Let's produce a graph of our new parent function, y equals cosine x. Same kind of values here, so I'll record that as negative pi. Maybe this is pi and 2 pi. I'll cut the half this distance right here, and I'll cut this distance in half, calling this negative pi over 2, and then putting the additional quarter pi's there. Positive pi over 2, and then 3 pi over 2 here. Just ran out of room to label those other tick marks. Notice the y values go as low as -1 and as high as 1, so similar to what we had over here. This will be +1, and perhaps this will be -1. Plotting, if you're comfortable, turn the video off, plot yourself. 7, maybe about right here. So now we're back up here. Graph's starting to come back down. At pi over 2, we have an x-intercept. 3 pi over 4, pi at -1, etc. At 2 pi, we return to a height of 1. Okay, thinking about the shape that we have here, we're going to kind of bend this graph kind of inward like this, and then eventually at this point we have to kind of bend back down. It really should be shaped kind of downward like this, and about right here. Oh, it's probably not far enough over. We come down, collect this x-intercept, and as we come down here, we kind of bend it back this way. No sharp turns, make it rounded. Coming back up here, and then it starts to peak out before it's going to return back down. Now, of course, I could show arrows on the ends of these to suggest that the graph doesn't just stop here. This is just one period that we have. We typically don't, but as long as we understand, that's good. All right, so this is a new parent function that we're going to be transforming in later lessons. All right, so what are some of the key points that we're going to use? What are 5 key points that we're going to use to assist us in doing some transformational graphing? Well, for cosine, instead of starting at 0, 0, we're going to actually start at 0, 1. Then we'll use pi over 2 and 0. Anytime we can use a 0 coordinate to work with numbers, multiplying, adding, working with 0 is wonderful. So pi, -1, etc. Okay, well, notice that cosine has the same period that sine has. So if I were to start looking at the cosine graph from x equals 0, how long does it take horizontally for this graph to start repeating itself? Well, right here at x equals 2 pi, I see that the graph suggests that I'm just going to repeat and create another cycle. So we say the period also for cosine is 2 pi. That's the horizontal distance needed to complete its cycle and start to go, repeat again. All right, so this is where y equals sine x and y equals cosine comes from that we looked up on the graphing calculator. All right, so additional information about these graphs right here, some new terms. The amplitude of a trigonometric equation, y equals a, that's going to be a number, a value, a times sine of x, and also y equals a times cosine of x. The amplitude represents half the distance between the max and min values of the function and is given by the absolute value of a. Okay, so amplitude, that's what we have to remember. What is the amplitude of y equals sine x? Well, according to this definition, if I look at the coefficient on the trig function, which is 1, if I found its absolute value, which is just 1, we could say the amplitude of the parent function y equals sine x is 1. Now, graphically, it's saying it's half the distance between the max and min values. All right, well, the max value is 1. The minimum value is -1. That vertical distance is 2. If I took 2 and divided it by 2, I would get 1. Another way to think about it is kind of a midline. Look at these 3 points right here that fall on the x-axis with y equals sine x. These 3 points right here are when we look at the 5 key points, these 3 points right here are kind of on the midline, someone might say. The midline. So we would have to go up 1 to reach our maximum. And then from the midline points, we'd have to go down 1 to reach the minimum. All right, so let's look over here. What's the amplitude for y equals cosine x? Well, from the equation, the absolute value of 1 is 1. Okay, the vertical distance between the high and the low y value is 2, and half of that is 1. So our amplitude is also 1 here for y equals cosine x. Let's practice with that. I have 4 examples here. Find the amplitude of each. Well, the amplitude here is going to be 4. That means that between 2 key points, instead of going up 1, I would actually go up 4. So I'm vertically stretching the sine x graph. Problem number 2, all we have to do is look at the a value. It's 2/3. So if we compare that to our parent function here, instead of going up to 1, I'd go up to 2/3, and that would be my max, and down to -2/3 would be my min. So it wouldn't reach as high, that graph wouldn't reach as high as the parent function or as low. So from an equation, it's easy to determine the amplitude. Okay, let's look at some cosine functions. What's the amplitude? 5. What's the amplitude here? 7. So for the cosine graph, instead of going up to 1, we'd go up from these midline points, so to speak, up to 5 and down to -5. It would be a great stretch on that, as would 4. Let's revisit what effect does negative have on a graph? Well, for number 1, for y equals -4 sine x, just to kind of get a preview into our transformational graphing, -4, the negative would actually have us start from the origin, but instead of going up, we'd go down, and we'd go down to -4, return, and we'd still pass through this point with that equation, and then we'd go as high as +4. So the negatives in front here, okay, have the effect of transforming or reflecting through the x-axis your graphs. All right, what else do we need to know before we can do some transformational graphing? Well, we need to be able to talk about what's the period. I've already kind of mentioned that. It's the horizontal distance from the beginning to end of one cycle. So if we have an equation like y equals a sine, and notice this new value, b, y equals a times sine of bx and y equals a times cosine bx. We know a is for the amplitude. Well, the coefficient on the x right here and x right here, we can call that value b. So a is the multiplier on the trig function, but b is the multiplier on the x. So what's the period of a sine or cosine graph? We can find it without looking at a graph by using this formula. So the period for sine x, okay, if you look up here, this coefficient is 1. We would take 2 pi, always 2 pi for sine and cosine, and divide it by b. So here a is 1 and b is 1. Well, 2 pi divided by 1 is just 2 pi. And we saw that graphically, that it took that distance for this graph to repeat itself. Same thing for cosine x. A is 1 and b is 1. So if we're asked what the period is, if we don't have a graph to look at for cosine, then we could just take 2 pi and divide it by whatever number's in front here, and then we can respond to the question and be done. Okay, well, let's look at some examples. It says, find the period of each. Okay, I see I have sine, sine, cosine, cosine. So this is the formula I want to use. So I'm going to take 2 pi, always 2 pi on top for sine and cosine, and divide it by b. So b is 2. I'll clean this up, divide the 2's out. So now my period is diminished to pi, meaning that this graph would start and stop its cycle, one cycle, at x equals 0 and end at x equals pi. So we can see that it's really been horizontally compressed. It's thinner. All right, so what would be the period of 2/3 times sine of 1x over 2? So here A is -4, here B is 2. The amplitude would be +4. The value for A is -4, but the amplitude would be called +4. B is 2. Here, A is 2/3. That's the amplitude. It's already positive. And B here is 1/2. It's 1/2 times x. So the formula to get the period for this equation, 2 pi divided by 1/2. Well, keep change flip, multiply by the reciprocal, and you're going to get 4 pi. So let's think about what that means graphically. Well, for this equation, its period would take a lot longer to occur than the parent function. So instead of starting here at x equals 0 and ending at x equals 2 pi, I would actually go up and down and only have half the period, but then I'd have to do the down part and end up over here at 4 pi. So we can see that B changes the x coordinates. Okay, A changes the y coordinates. You might want to think about that. And B changes the x coordinates of points on the graph. Right over here, A is 5. That's the amplitude. B is 3. So what's the period? Always 2 pi divided by B. That's the formula we're using for the period question. All right, so what does that look like? Well, that's not quite 1 full pi. So for this graph right here that's been vertically stretched by 5, it's also being made thinner. It's being horizontally compressed or shrunk. It would start at x equals 0 and end somewhere over here at 2/3 pi. Boy, that'd be like rough. You have to go up and down pretty quickly to finish because 2/3 pi is about right here. That's a horizontal compression. Right here, A is -7, but the amplitude is +7. And B is, notice B is 2/5. So what's the period? Well, it's 2 pi divided by 2/5. I'm going to bring up the reciprocal and multiply 2 pi by 5/2. That's gone. The 2's will cancel. It looks like I'm going to get 5 pi. Well, that takes a long time for that graph to complete one cycle. All right, in future videos, we're going to be transforming sine and cosine graphs by using the key points. We have talked about the values of A and B and their effect on the graphs. There's also some other transformations that can be applied to these trig functions, and those are indicated by C and D values. Kind of real quickly, C right here is going to suggest to us how to move a graph left and right. We're going to shift left and right. That will change, the C value will change the x coordinates if we move a graph left and right. It's also possible that we might be having to add or subtract a constant, and that's actually going to do a shift up or down. Shifts up and down vertically change your y coordinates. These signs could have been changed to cosines as well. I just left sine in all of these examples. Okay, what's the difference between this equation and this equation? We'll just notice that this D value, this constant, was just put up front. Whatever format you want. If you want to add the constant to the back end or if you want to put the constant up front, we'll kind of look at that in some specific examples soon. Also, if we don't have a horizontal shift left or right, then that would mean the value of C is 0. And if we put 0 in for C, then this equation right here would then end up looking like this equation. And then same thing here as well. All right, in future videos, we're going to use the key points for sine and cosine. We have them in front of us, good notes. Okay, and we're going to be using these formulas right here to generate new points on the transform graph. So yes, you will be given these formulas, but I have a feeling that through use, you won't need to be given these formulas. Okay, we can add them to our formula charts though. All right, these are formulas that are going to allow us to find new points on the transform graph. Okay, notice that in this x coordinate right here, that the x's change because of the b values and the c values. So what we're going to end up doing is we're going to be taking the key point x coordinates, multiplying those x coordinates by 1 over b once we identify it. And once we do that, then we're going to add any c value we have to get a new x coordinate. Here, to get the new y coordinate on the transform graph, We're going to take the parent function's key points, their y values, multiply by any a in the new equation. Once we multiply, then we'll add any d that might appear in that equation. We'll have a lot of practice with this in future videos.